Hello friends. In previous video, we have basically seen the implementation and time complexity about the Dikshitara's algorithm. In this video, we will see the last part from the graphs, that is a topological sort. So first of all, we'll understand what is a topological sort. So here, according to the definition, the topological sorting for a directed acyclic graph is a linear ordering of vertices such that every directed edge uv, that is edge from vertex u to vertex v, in that case vertex u comes before vertex v in ordering. So let us try to understand the definition of it. So first of all, very important thing about topological sorting is that this concept is only applicable for the graph having a directed acyclic. That means it is not applicable for the graph if the graph is not DAG. So what is the DAG? First of all, D stands for directed. So graph should have a directed edges. Second thing, it should be acyclic. That means there should not be a presence of cycle in the given graph. Such a graph we called it as a directed acyclic graph. So let us take a simple example here. So basically here this is a graph and this is a directed acyclic graph where the directed edges are there and there is no cycle present in the given graph. So basically what is a cycle here in this case? Let's say this is a vertex 6. Okay, so from vertex 6 I am going to vertex 2, from vertex 2 I am going to vertex 8, and let's say if from vertex 8 if there is a edge from 8 to 6, then there is a presence of a cycle. So then this particular graph we will call that this is a cyclic graph where the cycle is present. But now here there is no cycle in this graph, so this is called as the directed acyclic graph. Now another very important thing, basically what is the difference between the DFS and the topological sort. So in the DFS we print the vertex and recursively go for the calling its adjacent vertex and keep on printing. But in topological sorting we need to print a vertex before its adjacent vertex. So let us understand the difference. So here I want to perform a DFS on this graph and I'll start from vertex 7. So after vertex 7 I'll print, let's say, vertex 2, and then from vertex 2 I'll go to vertex 8. So like that way we will go for a DFS traversal. But in topological sort we will be starting with the vertex having the in degree as a 0. So in degree means total number of incoming edges. So here vertex 7, vertex 6 and vertex 1 having the in degree as 0. So we will visit vertex 7, then vertex 6 and then vertex 1. Then after that we'll go for the next. The adjacent of 7 is 2, so we'll visit 2, we'll visit 3. Then from 2 I can reach out to 4, so I'll visit 4, I'll visit 5 and I'll visit 2. So like that way generally basically we are visiting the vertices in the ordering manner. So that is the main difference between the DFS and topological sorting algorithm. So ideally speaking, the graph can have a n number of topological sorts, n number of topological sort possible for a particular graph. If it has a Hamiltonian kind of a concept, then it will have only one topological ideal sorting, otherwise it can have n number of topological sorts possible in the particular graph. Another very important thing is that the graph having at least a one node with in degree as 0 and out degree as a 0, then for that graph the topological sort is possible. So let us look at the algorithm for performing a topological sort. So now we'll go for the algorithm here. So first of all, first step to perform a topological sort in the given graph is, first of all we'll compute the in degree of every vertex in the given graph, and we are marking the visited node count, which will be 0 for every vertex. So these are the two initialized things we'll be doing, finding the in degree of each vertex and marking them as visited as 0. Then we are considering all the vertices with in degree as 0 and we are adding them into Q. Then we are removing a vertex from Q, that is we're calling for delete Q, and these are the three steps which we are going to follow. So first of all, let's remove first vertex from Q. I will increment its count by visited node as 1. So I'll mark the visited as 1. I'll decrease the in degree of adjacent node of a particular node which I visited with 1. So I'll decrease in degree of the respective nodes connected with visited node as 0, as decrement by 1, not 0. If in degree of a neighboring nodes after decrementing by 1 becomes 0, I will add the respective nodes into queue. Then again I'll repeat the process. I remove the next vertex from queue, that is I'll call for delete queue. I'll display that particular vertex. I'll mark that vertex visited, that is mark it as 1 instead of 0. Then I'll decrease the in degree of its adjacent node having basically some value of in degree, and if some of them becomes 0, then again I will add them into queue. So I'll repeat this above step 3 until our queue is not going to empty. And then if the count of visited node is not equal to the total number of vertex in the graph, then topological sort is not possible. So very important point here, we are making a count of visited nodes. Every time we are incrementing by 1, and that count should be equal to total number of vertex in the given graph. So if this is not equal, then we say that topological sort is not possible for a particular graph. So let us try to apply this algorithm on a particular directed acyclic graph. So we'll see now example. So this algorithm is very famous. This is Kahn's algorithm. Now I'll initialize first of all visited of all the vertex as 0, 0, 0. We are finding out in degree and entering the in degree of every node. So in degree of 5 is 0, 4 is 0. In degree of 2 is 1, 3 is 1, like that way. In degree of 1 is 2, in degree of 0 is 2. Then we have marked visited as 0, 0, 0. Now first of all I'll find out the in degree of the vertex which is 0. So there are vertex 4 and 5 having in degree 0. So I'll insert here vertex 4 and vertex 5 into queue. Then I'll call for delete queue. So I'll delete a 4 from the given queue. I'll mark 4 as visited, which is 1. Then adjacent to 4 are vertex 1 and vertex 0. So I'll decrement their in degree by 1. So 1 has in degree as 2. Now it will become 1. 0 has a 1 degree, 2. It will decrement by 1. So now both of them will have in degree as 1, 1. I will display 4. Then now adjacent to 4 were 0, 1, but their in degree is now not 0. So I'll not insert them into queue. The next I'll apply for delete queue the vertex 5. I'll display vertex 5. I'll mark vertex 5 as visited 1. Adjacent to vertex 5 are vertex 2 and vertex 0. So vertex 0 has in degree 1. I'll decrement it by 1. So now it will become 0. So I'll insert vertex 0 into queue. 2 has in degree 1. I'll decrement it by 1. So this becomes now in degree as 0. So I'll insert 2 into queue. Then again I'll call for delete queue. So 0 will get deleted. I'll display 0. I'll mark vertex 0 as visited. Then adjacent to 0, there is no other vertex adjacent to 0. So then again I'll call for the next delete queue operation. So it will call delete. So it will delete 2. I'll mark 2 as visited. Adjacent to 2 is 3 with in degree as 1. Now I'll decrement the in degree of adjacent node of 2. So 3 ka in degree now will become 0. And since it has a 0 in degree, I'll insert 3 into queue. Again I'll call for delete queue. I'll display 3. I'll mark 3 as visited. Now adjacent to 3 is 1 with in degree as 1. I'll decrement in degree of 1 by 1, so it becomes 0. So since in degree of 0, 1 becomes 0, so I'll insert 1 into queue. I'll call for delete queue. I'll delete 1 from queue. I'll mark 1 as visited. Then again next adjacent to 1 there is nothing. So now there is nothing to insert in queue. So queue becomes empty. Our algorithm terminates here. Now we'll count here the number of visited. Count 1, 2, 3, 4, 5, 6, which is equal to total number of vertex. So result here we get here is basically the topological sort for given graph. See here, there can be other topological sort is possible. First of all, we inserted 4, but instead of 4 I can insert 5, then I can insert 4, then I can consider now 2, I can consider 0, I can consider 3, I can consider 1. So there are different topological sorts are possible for the given directed acyclic graph. Now let us look at the time complexity of this algorithm. So here in this algorithm, if you find out time complexity, so time complexity basically comes here as O of E plus V, since we are here using a queue and visiting all vertex, and E is the number of edges. So provided actually this time complexity, we will get it by using the adjacency list. Now what are the applications of topological sorting? So very important application of topological sort is used to find out the deadlocks in given algorithms. So topological sort is used to detecting deadlocks. It is also used in job scheduling, specifically in pipelining the competing jobs. Then it is used for checking for a symbolic links. It is used for evaluating the formulas in the spreadsheet. So according to a particular ordering, whether the expressions are getting evaluated or not. It is also used for representing course prerequisite. So this is very important. So I want to do a course A, but before course A, I must do, let's say, course X. So it will basically visit X and then it will go for A. So for doing a representation of course prerequisite, the topological sort is used. Another very important thing, topological sort is used to resolve the symbolic dependencies in linker. So in linker we have external symbolic definitions are there and their local symbolic definitions are there. So to resolve those symbolic dependencies, the topological sort algorithm is used. So here we ends with the topological sort, and hence we end with the graph. So in the next video we will start with basically the hashing and hashing techniques. Thank you so much for watching.